maybe, hopefully. We'll start in another 2 minutes or so. We're very close to starting. Those of you who were at the math session yesterday or the CT session earlier today would know how this works. So in case there's anyone here who's new, you have to join on WebEx, and you also have to join on this joinpd.com. That's important. So you go to joinpd.com and then put in this code that you see on the top right, rvunsf. Okay, so it asks for the code. Put in the code, and then you will see it. And so I think for some reason on YouTube we are not able to get there's something blocking the code. So I don't know how to correct that. Maybe somebody can put a comment on the YouTube chat and put the code there as well. Joinpd.com and rvunsf. Okay, so that will help. It's very important that you do not enter any answer on the chat window on WebEx. Okay, don't use the chat window on WebEx only for questions you have, specific questions you have, subject questions that you have. Don't put any answers or anything on the chat window. All the answers you have to put on joinpd.com after you've entered the code. Okay, hopefully this is clear. So we'll go through problems one after the other. Please keep the your notebook and pen ready for solving. I'm getting a little distracted because I'm just trying to make sure all the windows are in place. Sorry about that. Keep your notebook and pen ready for solving problems. The moment you see a problem, I'll give you some time to solve. You can go ahead and use that time to solve. Okay, so let me just walk you through how your screen will look. I think many of you who've done this before maybe know how it will look. But still, I think it's good to go through and show you how it looks. So this is how a typical question screen will look. The questions will come on the left, and description of the problem and the actual question will come on the left, and then the actual question that needs to be answered will come in the middle, and your options will be shown on the right. Okay, if you're on a desktop, you will see a small box where you have to just enter the answer, and it will just come to us. There's no need to do any submit or something separately. If you're logging in through mobile, if you've gone to joinpd.com and you've entered this code and joined from mobile, you will see an answer question button at the bottom. Okay, you have to click on that and then answer. There's no submit, just enter the answer and we'll get it. Is that okay? So to practice this, so here's some screenshots. Let me just show you a couple of screenshots from how it will look. A typical question will look like this on the mobile and on the laptop or desktop. Okay. So to get ourselves started, here is a very simple test question that I put for you. If you're on joinpd.com, you should be seeing the answer box. Hopefully you can see that, and I can see there are responses that are coming in. That's nice. So yeah, keep putting your responses. I'll give you a few minutes, then we'll see. So there are some people asking for something on WebEx, annotate or something. There's no need to do any annotation on WebEx or anything like that. You don't answer the questions on WebEx. You have to go to joinpd.com. In your browser window, you open joinpd.com and put in the code rvunsf. When you do that, you will get a box and a view to answer this question. The same question will show up there and you can answer. Okay, so it's a very simple question. I've also kept this question up because we want to wait for people to come in. and the number of people coming in is trickling in slowly. We have to give about 5-10 minutes for people to join, I think. Let's give them that time. Also for people to get used to the connection, everything. Okay, so we'll give a little bit of time and then get started. Yeah, so people are answering in the chat window. There's no separate submit button. It's just a box. You simply enter your answer in that box and we get it. No problem. Now, don't put the answer in the chat box of WebEx. This is not the place to put the answer. Please go to joinpd.com, then enter your answer there. Okay? The chat box in WebEx is for asking questions. Any questions you have on the subject, something is not clear, something you want to go over again, or maybe give a different sort of feel for, that's what you use the chat box in WebEx for. Okay? So the week 8 deadline has been extended. It's up to Sunday, I think. Week 7, yeah, week 7 is on Sunday. Has the calendar been released? So apparently you have got a calendar. I think week 7 is Sunday and week 8 is Friday, right? The next Friday. Okay, so that's enough time. I think we also have a reasonable number of people who have come into the come into the session. So let me show you the responses. So I can click on something and show you the responses. Okay, so this is not working quite nicely. So let me just show you the grid. So 0.3, 0.3, 0.3, 0.5. Okay, so this 0.5. Quite a few people who put 0.5. So there's 0.17. Okay. Okay, 0.5. So I see 3 or 4 types of answers. 0.3, 0.6. Okay, so quite a few answers are interestingly incorrect here. So 0.333 is the correct answer. So let's go back and revisit this question and quickly discuss why 0.333 is the correct answer. So once I move out of the screen, you can't enter answers anymore. So I think it was a simple enough question. So the basic idea is this hint that is given here. So let me just quickly go through and discuss what it is. So these are questions where you have what's called a uniform distribution. Okay, and in the uniform distribution, the main idea to remember is this: what is put here. Okay, each outcome is equally likely. Okay, so I think is a pointer on WebEx. Yes. All right. So, so the important thing is each outcome is equally likely. So you just have to imagine a die being thrown, and then what are all the outcomes? There are 6 outcomes: 1, 2, 3, 4, 5, 6. All of them are equally likely. So once you know all of them are equally likely, computing probability for any event. The event that I put out here is the number that you see is a multiple of 3. So what are the multiples of 3 in this list? 3 and 6. There are 2 multiples of 3 in this list, 3, 6. So number of favorable outcomes is 2. Total number of outcomes is 6. So 2 by 6 is 1 by 3. And remember, you have to enter a decimal in the in the answer box. So you do 0.33333, whatever, 2 or 3 decimals. That's good enough. Okay. So remember this. This is extremely, extremely, extremely important. Anytime you have a uniform distribution, finding the probability of an event is a very simple idea. You just count the number of favorable outcomes and divide by the total number of outcomes. So sometimes you might have to count both. So you count, you're done. Okay. So that was a test question. We did spend some time on it. Some people have got 1 by 2. Some people have got 1 by 6. I don't know. Maybe they made a mistake. They maybe included one additional multiple or forgot one multiple. Okay, so it's likely. So notice there are two multiples of 3, 3 and 6. Okay. All right. So let's go to the next question. So this is like a prelude question. So we'll take very little time for it. So I'll give you only 2 or 3 minutes max. 2 minutes or 3 minutes for this question. You have to just read this question and answer it. Okay. So there is an urn. Urn is like a pot. It contains 5 blue balls and 8 red balls, and the ball is chosen at random. That's the question. So that's the setting. You can imagine what are all the outcomes. So what is the probability that the ball is blue? The ball that you chose is blue. So that's the question. And please put in your response. I'll give a couple of minutes. So people are asking how to enter answers. So if you're new to this system, how to participate, there's this information here. You have to go to joinpd.com. Okay, joinpd.com, and you have to enter this code RVUNSF. Okay, RVUNSF. So this is what it is. This session is not a general doubt clearing session. This is a specific session for answering, practicing question solving, graded assignment solving. Okay. If you've not been looking at your email and you've just attended this session, then this is for specific problem solving. It's not for general doubt clearing. You have to also participate. The way you participate is to go to joinpd.com and put in this code, and the question will come up and you have to answer. Okay. That's clear. All right. So I think I've given enough time. Maybe I'll give one more minute because I think people are still sort of coming in. Some people are new. Okay, so I'm going to show the responses. Once I show the responses, you can see the answer. Everybody is putting a decimal, and 0.38 odd seems like a powerful answer. That looks correct to me. Somebody's got 0.61. I don't know who they got that. Most people have got this 0.384, and that looks okay to me. 0.625. That doesn't look like a correct answer. So I'm going to describe the solution soon, but looks like many people got this answer. So I could do this other one, but it's usually it just doesn't give me control on. Or maybe you can zoom. Yeah. So it doesn't quite give me a good view of how that works. So let's proceed to look at the solution. Okay, so we're going to look at the solution. So I wanted to think about this carefully. So there is a pot. There are 5 blue and 8 red balls, and you have to think of outcomes and list out the number of outcomes. There are 13 possible outcomes. Okay, uh, depending on which ball is going to come out, right? So there are 13 balls there, and the outcomes are 13 in number, and 5 of those are blue and 8 of those are red. Okay, so this is the way to think about it, and uh, be convinced that this is how you have to think about it. There is a ball that's picked from an urn, and the urn has 13 balls. You have to put out all the 13. There are 13 outcomes, and each outcome is equally likely. So this conversion is very important to understand. And then once you do this, the blue ball is just favorable outcomes, right? So favorable outcomes is just B1, B2, B3, B5. And now we are in a uniform distribution. How did we know it's a uniform distribution, right? So if you go back and look at the question just said at random. Anytime someone does something, a selection, and the only thing that's mentioned in the problem is at random, there's no other information given, you can put down all the outcomes and assume a uniform distribution. Okay. So these are all like, how you translate an English sentence into the corresponding probability statement. Okay. So if someone says there is some things that I'm picking, I pick one at random, then what they really mean is I'm doing a uniform distribution on all the possible outcomes. Okay, so if you have an event that's favorable to you, you just have to count the number of favorable events divided by total number of outcomes. You get 5 by 30. Okay, so I put down all these things laboriously, but most people will just write 5 by 13. They'll see the answer question and they'll write 5 by 30. It's sort of, in some sense, it's obvious. It's not a very involved calculation, but I think it's good to know where it comes from sometimes, because if you get confused, you can go back to the basic definition. Okay, so quick solution. That was a prelude to question 1. Here is the second prelude to question 1. Once again, I won't give too much time. I'll give about 3 minutes or so and expect you to put down an answer. The question is sort of very dangerously similar to the previous one, except for this one little line here. I wish I could highlight it for you, but you can see, I mean, the first two lines are exactly the same, two balls, but no, not exactly the same. Second ball, second line itself is different. Basically, two balls are drawn. It's not just one ball. Two balls are drawn, one after another, at random, without replacement. So pay attention to every phrase here. All of these are important. Two balls are drawn. It's telling you two balls are being drawn, one after another. First one you pick up, the next one you pick up after that, and it says at random. So anytime you pick from whatever you're left, you can assume a uniform distribution. That's what at random means. And without replacement, that's also a keyword. Okay, so all these are key phrases. So when you read a problem in probability, you have to look for these phrases. When the experiment is being described to you, when the setting is being described to you, look for these kind of key phrases which are giving away how the distribution is going to work. Okay, so all these are key and pay attention to that. The first ball is red. Okay, notice that's given to you. Okay, you've been given that the first ball is red. Okay, note that down. It's very, very important. The first ball that you drew was red. Okay, and then here's the question: what is the probability that the second ball is blue? Okay, so put in your responses. And I'll give a couple of minutes more, and then I'll discuss. Okay, I see about uh, close to 75% of people have answered. I'll give one more minute. Okay, so let me show the responses. Okay, there's a popular answer which is 0.764. There's also 0.2124. That seems to come quite a bit. 0.2124. Okay, I'm intrigued by this 0.2124. I didn't get the 0.2124. Okay, 0.76 seems to be a popular answer. And I keep seeing this 0.2124, which maybe we answered probability that the second ball is red. I don't know. The question asks for the probability that the second ball is blue. I think, right? Not red. Maybe that's that gives 0.2, maybe. I don't know. But that seems to be a very popular answer. I think the answer is more like 0.764. I think that's the correct answer. So let's see the solution. So maybe if we see the solution, also 0.42 that's coming off in. Don't know why. This 2124 is troubling. I think where people got 2124 from. So quite a few 2124. And there is this 764. Okay. Right. Let me do a little check here. Where did 2124 come from? What was 2124? Can somebody maybe put a chat on the WebEx saying how they got 2124? I'm really intrigued. I would like to know if there is like a obvious way to. Oh, okay. All right. Okay. All right. So you're foreseeing the problem. Okay. Now I understand. Okay. See, this problem is slightly different from the problem that you're solving. Okay. So now I understand the misconception. See, the first ball is red. That's given to you. Okay. So in a question like this, when something is given, okay, the first ball is red. It's already there's no choice in the first ball. It's red. There's no probability there. Okay, so I guess the ambiguity was because of that. You got confused by that, and you put in a probability for that also. I don't want you to put a probability for that. That's given already. And the question is asking about why the second ball is blue. Okay, so anyway, so let me just go through and show you the solution that I had in mind. Let's see, look at that. See, the question I wanted was this conditional probability. Okay, so this ambiguity will always come, and one needs to be very careful. So the best way I could have worded this is, what is the conditional probability that the second ball is blue, given that the first ball is red? So that's what that would have been like an unambiguous, clear way of wording it. But sometimes people don't word it like that. Quite often, probability problems, when something is given, it's given, and you have to sort of. Uh, I know it's vague. I know many of you want to account for the first probability, but what is asked here is a conditional probability. Okay, so maybe that is something to be very clear about, and I'll think of that next time I phrase a question. So what I really wanted, what I had in mind was this conditional probability. What's the probability that the second ball is blue given that the first ball is red is given, right? So there's no need to worry about it. So you account for it and then you get after that it's the same calculation, 13 by 70. Okay, so I hope this is clear to people now. What I had in mind when I asked this question, maybe I could have been a little bit more clear in the wording, but this is what I wanted to write. Okay, so now having done these two, we are ready for the real problem. And I guess many of you have maybe solved the real problem also, but the number is different here. Notice there are 7 red and 13 blue balls. It's not 5 red and 13 blue balls. Once again, 2 balls are drawn one after another at random without replacement. Okay, same setting, but notice that first ball, no information about the first ball is given. Okay, no information about the first ball is given. And this is the probability. There's no conditional here. Okay, so this is just the probability. I'm not asking for conditional probability or anything. What is the probability that the second ball is blue? That's what I want to know. Okay, so once again, let me repeat and make sure. I think this question is not ambiguous at all. The previous one had that ambiguity. There's no ambiguity here. There are 7 red and 13 blue balls. 2 balls are drawn one after another at random without replacement. Okay, what is the probability that the second ball is blue? Okay, so this is just the probability. You have to answer the question. Okay, I'll give a little bit more time for this, and then maybe about 3-4 minutes, and then show you the results. Please don't use the chat box on WebEx for your answers. You have to go to joinpd.com. The how to participate information is on the top right. Go to joinpd.com, put in your code rvunsf, and then you can answer the question there. Please don't put the answer on the chat box on WebEx. So more than half the people have already answered. So this question about what happens on the first ball. So that's why I put a hint here. Okay, so you have to allow for all possibilities for the first ball, and then combine whatever probability you will get carefully. Okay, so yeah, yes, first ball might be blue, ball may be red. Both are possible. Okay, so people are still working. It's getting close to two-thirds of the people. More than two-thirds have entered the answer now. We'll wait for. Okay, where should we answer? Go to joinpd.com and then put in your code rvunsf. Okay, so I'm going to give one more minute and then I'll go into an explanation. One more minute, then I will give you the solution. And in fact, I'll give a very detailed solution on how to answer such questions. Uh, the my voice, I think, is okay. Balaji, can you check? Voice is
Yes,
okay?
sir. It is fine, sir.
Okay, okay. All right. Please check your earphones or headphones if voice is not okay. Okay, just I think people are still entering. Okay, yeah, more than 75% have entered. I'll just wait for 30 more seconds and then go on and give you the explanation. Okay, so let's see the responses. A very popular response is 0.65, and people are eager to uh, give explanations and why it is. Oh, there's an answer 1.3. Okay. Now, this is something you have to keep in mind. Okay, so why do I want to highlight 1.3? If your answer is not between 0 and 1, you already know you're wrong. Okay, so remember that all probabilities have to end up between 0 and 1. It's a very, very valuable lesson, and believe me, experts make these mistakes. So we always check whenever there's a probability to evaluate. The first thing to check is it between 0 and 1? If it's not between 0 and 1, then there's something wrong. So make sure you check it. There are a few other answers, 0.8 and then 0.06 and all that, 0.889. There's a question. Somebody who said 0. Okay. All right. So this maybe is the first time for some people seeing questions of this nature. So what I'm going to do is show you how to answer questions like this. Okay, so this is sort of like a general method that I use when I'm faced with the problems like this. This is how I do. Maybe I don't write down all these steps in great detail. I probably will do half the details in my head, but that's right now. But if you're starting out and if you're doing probability for the first time, I would strongly suggest that you write down all these steps. Okay. So the situation is quite clear. The event is second ball is blue. Okay. So the first thing you have to do is see there are two balls. First ball is drawn, second ball is drawn, and you have to sort of incorporate what happens to the first ball and write out the whole event in a complete way. Okay, so properly you have to write it down. Okay, so you have to incorporate what happens to the first ball, right? So first ball happened first, only then the second ball happened. Okay, without knowing what happened to the first ball, you're not going to be able to do any probability calculation of the second ball. So you have to incorporate what happened to the first ball, and this is one way of doing it. Okay, so notice what I've done here. I've just exhaustively gone through what can happen with the first ball, and I've written down the event second ball is blue. Okay, so there are mathematical ways using set theory and all to describe this, but I'm just doing it in English. uh, so uh, so you can write it like this, right? So first ball can be blue and the second ball can be blue, right? So this is one possibility. Or notice this or and here, these are not idly used terms, they are carefully used terms. Be careful about where you put the and or, right? So the and is both of those things should happen, right? So first ball should be blue and the second ball should be blue. That's one possibility. Or first ball is red and second ball is blue. Okay, so I'm going to take a little longer to go through this explanation, just to make sure that people who are not used to these calculations can sort of follow where these things are coming from. So this is always the first step. So write out the event. Event will usually be about some partial something. So you write it out to include all the action that happened in the experiment. Okay, so that it's complete and you can fully describe it. So notice first ball has to be blue or red. So I can stop here. There's no one more or, right? So that's it. First ball is either blue or red. You can stop here. So this is the first step. Make sure you understand steps like this very, very clearly. So write out an event in terms of other events and combine them using and or. Okay, so this is the first step and a very crucial step. It's like I said, most people who have practiced would do all this in their head, but if you're seeing it for the first time, it's good to write it down explicitly. All right. So what happens after this? There are rules. Okay. So combining events and calculating probability for them, there are a set of rules. Okay. So these are what I've put down here are the most elementary rules, and we will add a few more rules. And these are the only rules you'll need. You'll need like hardly like 4 or 5 rules. That's it, and you can use them over and over again very carefully, and then you can compute probability for any event combined in this fashion. Okay, so these are the rules, and there's no magic here. You have to just use these rules. So for instance, I've put here probability of empty event equals 0. Okay, it seems very obvious, but you'll see this empty event is sometimes difficult to find out. I'll show you why that works. Then probability of a sure event. Okay, so you know for sure that this is going to happen. That's going to be 1. And then there are these 2 rules, one for or and another for and. Okay, so I'm giving you these rules. These rules are very important. So the or rule is a little bit long. Okay, probability of event 1 or event 2. It's going to be probability of event 1 plus probability of event 2. And notice this minus. There's a minus probability of event 1 and event 2. Okay, so that's the or. It's a little bit long-winded, but it's very important. Okay, and has a rule through conditional probability. Okay, so this rule is important to know. Probability of event 1 and event 2 is probability of event 1 times probability of event 2 given event 1 has already occurred. Okay, so this is the conditional probability. So how do you find the conditional probability? We did that in one of our previous examples, right? So how did we do it? If you want to do conditional probability of event 2 given event 1, you account for event 1. Okay, so you take the outcomes that can only happen within event 1, change the possible outcomes, and recompute the probability for event 2 using the modified set of outcomes. So for instance, why do I say modified set of outcomes? So in this case, for instance, if the first ball is blue, then the number of blue balls changes when you draw the second ball, right? So you have to account for that change. So make sure you make the change, and then you compute probability for event 2. Okay, so this is how you do conditional probabilities. Okay, so these rules are enough for this problem. Okay, and we will add a few more rules, as 1 or 2 more rules after this. This will help you, but make sure you're very clear on how to combine events. Write one event in terms of a combination of all that can happen, and then once you've written it as a combination of and or, how to evaluate the probability using these rules. Okay, so these are the rules. Make sure you know them, make sure you understand them, make sure how you know how to use them. Okay, that's what's most important. Let's see how to use it in this case. Okay, we're going to apply the rule. At the beginning, we had 7 red and 13 blue balls, right? This is what was there in the urn in the beginning. We wrote this event B2, which is second ball is blue, as first ball is blue and second ball is blue, or first ball is red and second ball is blue. So this is how we wrote out this event. Okay, B2 became B1 and B2 or R1 and B2. Is it okay? You saw this. So now I want to find probability of B2. This is the probability of one event, which is B1 and B2, or with, there's an or with another event, which is R1 and B2, right? So you use event 1 or event 2 rule. What is event 1 or event 2 rule? Probability of event 1, B1 and B2, plus probability of event 2, R1 and B2, minus probability of event 1 and event 2, okay, which is B1 and B2 and R1 and B2. Is that okay? So you use that rule. There's nothing fancy here. You have event 1 or event 2, you use the rule. That's it. Right? It's very simple. Now notice I told you this empty event is sometimes difficult to recognize. This B1 and B2 and R1 and B2 is actually empty. Why is that? This is saying the first ball should be both blue and red. That's not going to happen, right? First ball is either blue or red. So this is actually an empty event. So you have to be able to identify these empty events. This is very important. Okay, it seems very simple, but as you see more and more complex events, you see this. So many experts, including your instructors, including your faculty, will forget this minus term. I've seen so many experts forget this minus term, and when you forget this minus term, you will go wrong. Okay, so in this case, it's okay. Minus term is 0. So it's an empty event, so that goes away. Okay. Now, what about probability of B1 and B2 and probability of R1 and B2? You use the AND rule. What is the AND rule? It's P of R1 times P of B2 given R1. Okay. And now we can calculate. Everything here is easy to calculate. What is P of R1? What's the probability that the first ball is red? 7 out of 20, right? This is just a uniform distribution. And given R1 has happened, given that the first ball became red, okay, account for it, change the outcomes. You have only 6 red and 13 blue balls. What's the probability of blue? 13 by 19. Okay, so that's what you get for R1 and B2. Now, what is the probability of B1 and B2? You go through a similar calculation, you'll get 13 by 20 multiplied by 12 by 19. So you plug all these in, right? It's 7 by 20 into 13 by 19 plus 13 by 20 into 12 by 19 minus 0, of course. You will get 13 by 20. Okay, so that's your answer. I know I went through this very, very slowly. We took a little longer than we thought, but believe me, this is how you have to do the calculation for these things. There are these rules for how to calculate probabilities when events get ANDed and ORed. You have to use them brutally, and you have to get the answer. Okay, so I'm going to spend just 3 more minutes. There's so many questions that somebody is talking about how Andrew should not teach AND rule. I don't know. It's a good comment, I think. But no, let me just, there was a question about this minus term. So remember, so let me just go back to the previous slide. So the rule is this. The rule is this. This rule, I don't know if you can see a proof for it in your statistics 2 class. Maybe you'll see a proof for it. But this is just accept it as a rule. Okay. If you have, in any case, you have event 1 or event 2. Okay. The rule is it's equal to probability of event 1 plus probability of event 2 minus probability of event 1 and event 2. Just put event 1 and event 2. That's it. This is a rule. Okay. Just accept this rule. And then just use it when you have this event, right? So the event you have is B2, which you have already written as B1 and B2 or R1 and B2. Okay. So B1 and B2 or R1 and B2. Okay. So you have event 1, which is B1 and B2. So notice event 1 itself is a complicated event. It's not a very simple event. It's B1 and B2. It's not just B1 or something. Okay? So it can be like that. You can have a complex event or together. So you have one event or with another event. You just use the OR rule. Okay, probability of B1 and B2 plus R1 and B2 minus B1 and B2 and R1 and B2. So those of you who know, technical details of unions and intersections, yes, this OR rule is nothing but the probability of union of two events, which is probability of the two events added minus probability of their intersection. Okay, and once you have the AND, notice this how to identify empty events from AND. That's also critical. See, B2 and B2 is not empty. Okay, B2 and B2 will be B2 happily. There's no problem. Okay, you're intersecting corresponding things. But notice what happened to B1 and R1. That's going to give you zero intersection. Okay, because the first ball is blue and the first ball should be red also. I mean, that's not going to happen, right? So this is logically it's not going to happen. Those two, like somebody is pointing out, are disjoint events, so the intersection will go off to empty. So you have to sort of identify these things. So this hopefully is clear enough. I did see one question where somebody is trying to do combinatorial calculations. I don't want to address it at this time. 13 by 20 is definitely absolutely the correct answer. You have to go in and check why these C2 type calculations are wrong. It can be a bit misleading. We will take it up maybe later at the end. Okay. So as of now, this is the solution, and I will be, at least every time I discuss a problem, I will follow this method. I will take the event, I will write it as and or etc. I will follow the rules. Okay, so I will follow rules. I'll write down the rules for you, so that there is like this one method you can use for any problem, right? So you will hardly go wrong if you do it like this. Okay, at least over the years, in my experience, I've seen this is a good way of solving it. Okay. So we are out of time. I would ideally like to take some questions now, but we're really out of time. So let's push ahead to question 2, and here it is. Okay. So if you can wait, let's finish all the questions and then come back and discuss the first question if you have any doubts still. So here's question 2, and once again we follow the same method. Go to joinpd.com, put in your code rvunsf, and you can answer this question there. So don't answer the question on the chat. Put only technical questions, subject questions that you have in the chat. Okay. So the question describes a slightly different situation. It describes a population where you have two genders, 45% are female gender and 55% are male gender. And it gives you conditional fractions. Among the females, 9% are left-handed. Among the males, 11% are left-handed. There are ways to interpret these things. When somebody says among the females, 9% are left-handed, you have to interpret it as a conditional probability. Okay. So these are things that, it's understood from the English, how to translate it into probability. But remember these rules. So 45% are female, 55% are male. That's just probability. Okay. If somebody says among the females, 9% are left-handed, they are giving you a conditional probability of left-handed given female. That's what is being given there. Okay. And you choose a person at random, and you have to calculate what is the probability that the person is not left-handed. So here's a new rule. You will need a new rule for this. So far, I've not told you what not is. Not of an event. If you want to find probability for not an event, it's 1 minus probability of the event. I'll describe that during the solution. Hopefully, you've seen that in your class. So use that and try to work out the answer. Okay. So once you've worked out the answer, you can put in the your response. So again, enter it in decimal. You can use 3 decimal places. Okay, so I see the number of responses is slowly inching towards the 50% mark. Once again, go to joinpd.com and put in the code rvunsf and enter the answers there. You'll see a box there in this slide, and you can enter the answers there. Do not put the answers in the chat box. If you have any technical question, you can answer that. Okay, about two-thirds of the responses have come in. I'll wait for my usual 75% thing, or the time. I think there's still 2 more minutes. We are inching towards 75%, but maybe not everybody has figured this out. Once again, if you find probability that the person is left-handed, go ahead and do that. The probability that the person is not left-handed is just 1 minus that. Okay, so you can calculate it either way. So should be okay. Okay, so I'm going to show responses. Let's see what the popular answers are. Okay, so at this point, 899 and 101, I can see where the confusion is coming from. One of them is 1 minus, right? So instead of answering for not left-handed, some people answer left-handed. So not left-handed, I think is 0.899. The probability of left-handed is 101. So this 1 minus confusion is always likely to happen. But 899 seems to be a very popular answer. There are other answers as well, 0.46, 0.6, 8. I don't know where to get that from. Okay, so there is some variety, but mostly people have given 0.899. So that's good to see. So let me walk you through the solution. I'll introduce you to this other rule which we didn't put down. Okay. Uh, okay. So we'll do that. But before that, let's write out the event, right? So uh, let me not jump the gun and write it exactly like before, right? So this not left-handed event, right? I want probability for not left-handed. I'm going to write it exactly like before. So it's going to be male and not left-handed, or female and not left-handed. Okay. So this is the way in which you write it. Okay, it's the same as before. So I've used the shorthand here. I mean, this is also very common in probability. People use shorthands for these things. M and NL or F and NL. Okay, so it's clear what the notation is, right? So this is just a shorthand. So once you do this, you just use the rule, right? So you apply the rule, except for this new rule for not. Okay, probability of not some event is 1 minus probability of the event. So probability of NL is going to be 1 minus probability of N. Okay, so that's the idea. So once you do that, it's easy to write down. right? Probability of NL is probability of M and NL plus probability of F and NL minus probability of the AND of the two things. Now, in this sample space, M and F, it cannot be both M and F, right? So that's how the sample space has been defined. 45% is female, 55% is male. So M and F ends up being empty. Okay, so that becomes an empty event, and that probability goes to 0. And when you come back here, now you use conditional. Okay, it's just standard conditional, the same event for M and L. M P of NL given M. Now this is given M, you know the probability of L. What is probability of L given M? That is 0.11. So you do 1 minus that, you will get 0.99. Okay, so here once again there is this same logic you use here, except for this not event being 1 minus probability of event. So you do 1 minus that, you get your answer. Okay, so hopefully that was clear. Some questions. Okay, so lots of questions that are out there, which maybe the instructors are better placed to answer. Uh, there's a question about two people are selected. What is the probability that both are not left-handed? Okay, you'll have to now write longer and longer events. So when you do the calculations, people are saying they need more explanations. Okay, so people are writing all sorts of other things. Okay, so I don't want to address that. Okay, but I don't think there's any major technical doubt on this calculation. It seemed simple enough. So once again, I'll emphasize this. Follow the same process when you have to compute probability. Write down the event, if necessary, as a combination of and, or, etc. Just follow the same process, and learn to recognize what probability has been given to you. Sometimes what will be given as a conditional probability, sometimes what will be given as a probability. From the wording of the problem, you have to recognize that. Once you do that, you're done. Okay. So that's the end of problem 2. So let's move on to a prelude to question 3. Okay, this is a trick question. I've deliberately put here, and I've also told you it's a trick question. And I want you to write the answer to this. Question situation has been described. A student writes an exam with two sections. The probability of passing section 1 is 0.8, and the probability of passing section 2 is 0.9. This has been given a bright student who's going to pass with good probability. What is the probability that the student passes both sections? Okay. Uh, so I have put here, it's a trick question. I'll give you a few minutes, really like 1 or 2 minutes to answer, and then we'll see the responses. Okay, go ahead. I'll give just 1 more minute. Like I said, the emphasis is this is a trick question. Consider the problem carefully and put in your answer. And then I've said enter in decimal. You can also enter text here. You can see that it's a big box. You can put in an explanation for what you think of this question. Okay, so more than 50% of the people have answered, and I don't want to spend too much time on this question. So let me see the Explanation, look at this, 0.72, such a popular answer. Oh my God. Okay. All right. So here's my solution, right? This, a question like this, I would answer like this. Okay, and I leave it like that. Okay, I don't want to write anything else, right? So why is that? Look at my rule. My rule says probability of section 1 pass is 0.8, section 2 pass is 0.9. I'm being asked for section 1 pass and section 2 pass. My rule wants a conditional probability which has not been given. Okay, this has not been given. So now what happens is many people who teach probability and statistics will give a question like this, and they will expect that the students make an assumption. Okay, they'll say you have to assume something called independence, in which case you assume these two sections can be passed independently by the student. The events are independent, so you can drop the conditioning and you assume 0.9 to be the probability for the next one. But I would say this question is wrong. Okay, if I were teaching probability in a class, I will never ask a question like this where you have to assume independence of two events which has not been given in the problem. If the problem does not state the events are independent, events are not independent. In fact, if you think about it, even from a philosophical point of view, if somebody is writing an exam, they've done section 1 really poorly, right? Won't it affect the section 2, right? On that day, I mean, it's not even clear that you can make that assumption, right? So you should not assume what's not given in the question. But let me also say this: a lot of people who teach probability will give such a question and expect the student to assume independence, and it's dangerous to assume independence, and it need not be true. In fact, you can have any probability for the intersection when the two probabilities are 0.8 and 0.9. Okay, so it's dangerous to assume independence. You should not assume independence, and in fact, if somebody is expecting you to assume independence, you should protest also. Okay, so at least in a question, that's what you should do. Okay, so independence has not been given, so the rule has expects a conditional probability, and the conditional probability has not been defined in the problem. If the problem defines probability of section 2, it does not define the conditional probability. Okay, so keep that in mind. So let me just modify this question where I've said here the events of passing section 1 and 2 are independent. I'm going to give you that now, right? So now you can use independence. Okay, now you can use independence, and then the question of passing both sections can be quite easily answered. People are now happily entering the response. Now, this little line here, the events of passing sections 1 and 2 are independent, that's given in the question. That makes all the difference between these two calculations. So I'm going to now jump to the solution. Thanks for putting in the response. You don't have to really put in the response here. I think I can see quite a few people have put in the response. So I'll give you one more rule. Okay, so here's the rule. If event 1 and event 2 are independent, when do you say event 1 and event 2 are independent? Probability of event 1 and event 2 equals the product of the two probabilities. Probability of event 1 times probability of event 2. This is the definition of two events being independent. Okay. So in this case, you can also bring one of these event 1s below and then rewrite this as probability of event 1 given event 2 being equal to probability of event 1, or probability of event 2 given event 1 being probability of event 2. Okay. So this is the independence rule. Okay. So the independence rule is sort of like somebody put subconsciously used by a lot of people, but quite often independence is not true. There can be a situation where it's very deceptive. You want to assume independence, but it's an assumption. You have to state it very clearly. So unless you assume independence, you can't directly write down the solution. But once independence is given to you, probability of passing in section 1 and passing in section 2 is simply the product of those two probabilities. You get the answer. Okay, so it's just a quick prelude. I wanted to go through it very quickly. It seems like there's some questions about this. Independent questions without writing it. Yes. So you may find a question that our instructors ask you, our faculty ask you, where you will be asked to assume independence. They should state that, or at least in class they should make it very clear. If you have to assume independence of event, assume. So it's at least in my classes I don't do it, and I think it's wrong to say that as well. Right? So you have to state two events are independent. It's not obvious. It's not given that two events should be independent. Right? It's the non-independent is definitely possible. Okay, but this, you have to live with this difficulty, because there are a lot of people out there who teach probability in so many different ways, and they will just assume independence happily. and they will not put it out in the question properly. I think that's not the right thing to do, but I mean, life is imperfect in such sense, right? So you have to live with it, and but expect the independence to be there in the question. Don't assume otherwise. That's my message at least. Okay. All right, so let's jump to question 3. Okay, I've given enough prelude. Uh, this is uh, this is a slightly more complicated question, but it uses independence, and it has been explicitly stated in the question that these are independent events. Okay, a student appeared for an aptitude test for a company. It had 3 sections, and passing now is a little bit more complicated. Okay, the student will pass the aptitude test if he passes in either section 1 and 2 or section 1 and 3. So it's like passing section 1 is definitely required. You could either pass section 2 or section 3. So that's the event here. And there are probabilities given. And I have stated explicitly that these are independent events. But quite often you'll see many people will give this problem without stating that these are independent events. Okay, they'll expect you to assume that, which I think is a very ambiguous way of asking the question. It's common. Many people ask this. Okay, so you have to sort of live with this. So my hint is for you to write out this event carefully, use the event rules very, very carefully. Don't forget the minus term. Be careful with what happens to the minus term and write it, use the independence and give an answer. Okay. So the question is sort of slightly twisted, as in you have to find P if the probability of passing the aptitude test, the final probability of passing the aptitude test is 1 by 3. Okay, so that's the question. Go ahead, I'll give you about 3-4 minutes, then we'll give you this. There's a question on what is the probability of passing section 1. So it's given as a variable P, okay, and you have to find P, okay. So the question asks you to find P. It's sort of, you could have asked it the other way around, but it's just, when you assume it's P, go ahead, do the calculation. Finally, when you write the equation, it will get a value. Okay, so people are making slow progress here. It's a slightly more twisted problem, I think. You have to consider the case of passing in all three. You have to consider every possibility, right? See, when you write out the event should be completely described. Student may pass all three, right? That's also okay. It's allowed, no? Not disallowed. Right? Right, the 50% of the people have now responded. Join PD. Please wait for 2 more minutes. It is slightly more complicated problem. You can imagine so many people are going to forget one minus term. Yeah, I think people are finding it a little bit more difficult than usual. Maybe we've not come to the two-thirds mark yet. Once again, if you're joining in late, to put in the answer to this question, please go to joinpd.com and put in the code rvunsf, and you'll be able to answer this question there. So please answer the question there. Okay, so people are slowly inching away towards the two-thirds mark. So maybe we won't hit the two-thirds mark. I don't know. Let me give 1 more minute. This is a slightly more difficult question. So let me give Tanmay has a question which seems. How many more questions are there for today? Just one more question after this. After that, we'll be done. So I want to give 1 more minute. I think many people are working on it. Let's hold on. Passing of third section in first case. What is first case? Passing of second case. Second case is. Oh, okay, okay. Yeah, so I think sort of what Tanmay is asking is also similar to saying, what if somebody passes all three? Right? It's okay. If they pass all three, they pass, right? They will violate the condition. That's how you interpret it. Okay, so I'm going to show the solution and then discuss it. Quite a few people seem to have got this 0.57, and there's also 0.66 showing up. 0.57 seems to be a very popular answer. Very popular answer. Okay. There is 0.667, 0.66 coming here and there. 0.5714 is dominating. So how can someone put out 0.5714? Tell me how they got there. Is there a quick expression that you can write out in the chat box maybe? I would like to see how you got 0.5714. Curious, because it seems to have quite a bit popularity. How did you get 4 by 7? Where did that come from? Oh, okay, okay, okay. Oh, all right, all right. So even after I told you, okay, so let me just okay. So I think I got it. I got it. I got it. I got how people got this. See, I gave you a rule for OR, right? I gave you a rule for OR. When you do probability of an event, uh, event one or event two, what is the rule you have to follow? It's probability of event one plus probability of event two minus probability of event one and event two. Did you take that minus into account? So you say p by 4 plus p by 3. I think I said some 4 5 times. Don't forget the minus. Don't forget the minus. Don't forget the minus. I think I said that so many times. Okay. So the rule is the rule, right? So you can't violate the rule, and it's all not always true that the AND event will be empty. Okay. So here is a case where uh, you know that's why I think somebody asked a question. Can somebody pass all three? Yes, you can pass all three. It's possible, right? You can pass all three. That's the event is given as P 1 by 4, 1 by 3, right? And they're independent. What's the probability they'll pass all three? P into 1 by 4 into 1 by 3, right? So, so that's the point I was trying to say that you have to be careful about, and you can see from the response quite a few people have put 0.57. So they've forgotten that minus, and that's not the correct answer. Okay, so so that's what it is. So my solution also goes like that. Once again, you can see I'm using the same method for every question. Okay, so I'm not going to change the method just because the question is different. I write the event out in its full detail. Okay, then I put a shorthand. I usually write it in shorthand like this. It's not very difficult to see why this is useful. Pass one and pass two, or pass one and pass three. And then you use the rules. Okay, after that it's the rule. The rules take over. Once you write like this, it's the rule, right? You don't bring in some other consideration like, do I consider all three passing, this, that, and all. You're not allowed to say all that. You write the event out and properly, and then the rules take over. That's a good way of doing it. You can bring in your intuition afterwards and see if the answer makes sense. Okay, so if you do that, pass 1 and pass 2 plus pass 1 and pass 3 minus pass 1 and pass 2 and pass 1 and pass 3. What is this? Pass 1 and pass 2 and pass 1 and pass 3. Actually the same as pass 1 and pass 2 and pass 3. And notice these three are independent events, right? They've been given to be independent events. So what's the probability of that? It's not zero. May not be zero, right? It can be, it's the product of the three probabilities. They're given as P into 1 by 4 into 1 by 3. That's P by 12. That's probability of that is P by 12. Okay. Similarly, pass 1 and pass 2 is P by 4, pass 1 and pass 3 is P by 3, that's okay. So probability of pass is P by 4 plus P by 3 minus P by 12. That's P by 2, and that has to be equal to 1 by 3. P has to be 2 by 3. So, okay, so it's a subtle little thing, but pay attention to these minus terms, okay? I know many experts, many people who teach probability will probably forget this, and it's it's okay. I mean, it's not like a grave offense or anything, but you get an incorrect answer. You miss out on one fraction, which makes a big difference. Okay. Hopefully, this problem was good and useful to you. So we're going to move on to the. Somebody wants an explanation again. So see the explanation is okay. So maybe you missed the first part of the presentation. Uh, the rule we follow is the OR rule. Okay, so what is the event that we want to find probability for? Probability for event 1 or event 2. Okay, so that's the probability you want to find. Okay, there's no there's nothing more here. So it's event 1 or event 2, and there is a rule for this. Okay, event 1 or event 2 is event 1 plus event 2 minus probability of the and of the two events. That's the formula. So why does this come about? Why do you need this minus, right? So if you're wondering why do you need this minus, remember you here when you find probability of pass one and pass two, you're sort of counting the case where one and two are passed, right? So yeah, Sharda Shruti has given an answer. So in the second term also you're counting the case where 1 and 3 are passed. Now it may happen there are cases where all 3 sections are passed. It gets counted both in the first term and in the second term. Okay. So you count both, okay, but you're double counting. So you have to subtract the intersection once. Okay. If you do that, then you get the correct answer. If you don't do the subtraction, you're over counting. Okay. So you've counted that intersection. That's all. Okay. Hopefully this explanation is useful. I mean, if if you can think of these logic, it's good. It's good to know the intuition as to why these results come. But or else, I mean, if you just want to solve the problem without thinking too much about all these things, you can just use the method, right? So the method will not cheat you. You put event one or event two, and blindly use the method, it will work. Okay. Okay. All right. So let's move on to the next question. We are also keep mindful of keep some eye on the clock. Okay. So we're going to go to question four. Question four is the last question, and there is a prelude to this question. Okay. I don't want to jump into the question directly. I'm giving a prelude here. The prelude is this. Okay. This is the first problem. Hopefully you can read it. There's like a machine making screws, and there are 3 different machines. And conditionally, some of the screws turn out to be defective. And if you pick a screw at random, which could come from any one of these 3 machines, some split like this, you need to find the probability that it is defective. Okay, so this is the question. It's a prelude. We'll eventually work our way to Q4 and then we'll stop. But let's do this prelude. I'll give you about 2 or 3 minutes. So, by the way, don't get confused by the way the English is worded. I mean, people say it is known from past experience, 1%, 3%. So how do you read these things? What is the meaning of this? So, when they say it is known from past experience that say 1% of the screws will be defective if made by machine one, what all they are telling you is giving you a conditional probability. Probability of screw being defective given that it came from machine one is 1%. So don't worry about the wording and all this. So you've got to sort of see the English and pick up the probabilities that it's defining for you. Okay. So this is sort of the way in which you can model how things are working. Okay. So from if a statement like this, you have to pick up the conditional probability of defective given that the screw came from machine one, screw came from machine one to be 1%. Okay. So if you joined very recently, don't put the answer in the chat box. Please go to joinpd.com, put in the code rvunsf and enter the answer there. Please don't put the answer in the chat box. Chat box is for asking questions, technical questions on the content. There's a question from Aditya on combinatorics and probability. So I mean, it's going to be a long-winded answer. It's maybe not directly connected to these problems. Maybe after these problems are over, I'll make a few comments on that. Okay, so I see some responses. Maybe there's some confusion. I won't take too much time with this question. It's only a prelude. So let's go in and see how to answer this. Again, the same method. Okay, so before that, maybe I should see the solutions. I'm sorry. So many people put in solution 0.023 seems like a very 233.88. Okay. Once again, I want to remind you, if you get an answer for a probability which is not between 0 and 1, immediately you're wrong. Okay, so check your calculation, check your understanding of what you're saying. Probability has to be between 0 and 1. Okay, so 0.023 seems like a very popular answer, and that's correct. Now 0195, okay, I think 0.023 overwhelmingly is the answer. So that's the correct answer. And let's see how to do that. Once again, I mean, it's the same thing. I mean, you may get bored after a little while looking at how this is working, but there's one little twist here. Okay, so I'm going to say screws defective is DEF, and M1, M2, M3 came from mission 1, mission 2, mission 3, and my defective event is M1 and defective, or M2 and defective, or M3 and defective. Okay, so now this is the first time we are facing a situation where you have the ORing of 3 events. Okay, yeah, how to approach 3 OR? That's a great question. Okay, so that's the same question I'm also asking you. How do you handle 3 ORs? Okay, so it turns out there's one special case where 3 ORs can be very easily handled. Okay, so what is the special case? The special case is disjoint or mutually exclusive events. Okay, so if it turns out that event 1 and event 2 is empty, event 1 and event 3 is empty, and event 2 and event 3 is empty. So these events are mutually exclusive or disjoint. Okay. If it turns out that these events are disjoint, then here is a rule for you to remember. Okay, this is an important rule, and in fact, this is one of the axioms of probability. Probability of event 1 or event 2 or event 3 when the 3 events are mutually exclusive is simply the sum of the 3 events. Okay, so the OR of 3 events is easy to handle when they are mutually exclusive, when they are disjoint. Okay, now there is an answer box in this slide. I want people to answer this question: what if they are not mutually exclusive? How will you handle the OR of 3 events when they are not mutually exclusive? Can you type in your response in the response box in this window? Okay, so you have a response box in this window. I want you to type in a response for how will you handle don't put it in the chat box on WebEx. Please go to joinpd.com, put it in the answer box there. How will you handle the situation if you don't know that event 1, event 2, event 3 are mutually disjoint? Okay, disjoint or mutually exclusive. If you don't know that, how will you do it? Okay, I'll give about a minute. I'll wait for about 5 or 10 more responses and then go out. Okay, so it turns out, let me not spend too much time on this. We're also running out of time. So, what is E is equal to mc squared by Einstein? What's going on here? Somebody is giving a funny answer, I think. Okay, yeah. So I think you can see here, there's some good answers have come in. Let's just see. Wait. Let me go for. Okay, yeah. The inclusion exclusion principle is what you have to do, but nobody has put it out fully or completely. Okay. Okay. Anyway, so there is a formula for it. There is a rule for it. Okay. I think this person has come closest to the rule, but the final minus is a plus. I don't know who this is. Whoever gave this response, the final minus is actually a plus. You do a minus for and then finally you put a plus for the all 3 intersection. Okay. So good. I think so. There is a rule for handling 3 intersections, but we have the disjoint case, which is very nice. So in fact, in our case, if you look at it, right, our event is the OR of 3 events, but these events are disjoint. Okay, so if you look at these 3 events, they're disjoint. You can quickly check, right? So why are they disjoint? If you take M1 and def and M2 and def, you want one screw to have come both from mission 1 and mission 2, right? That's not going to happen. So it's a mission. The one screw either came from mission 1 or mission 2, right? So that's the disjoint event. Once you have disjoint, you have to just add, and adding is very easy. All right, so the prelude, I took more time than needed, but I think at least one new idea was introduced in the prelude, so it's worth doing that. All right, so let's go to prelude number 2. Okay, so this is something called Bayes rule. Okay, so Bayes' rule uh, is again a new rule. It's a very simple rule, but it's very commonly misused, and no, it's also very well used by a lot of people. So this prelude problem number prelude true to question 4 uses Bayes rule. That's the hint, and here I've put the conditional probability also, right? So what's the conditional probability that the person is male, and I put that in brackets to be very, very precise. Okay, so I'll give you a couple of minutes and show the responses on that. Once again, put your responses on joinpd.com, put the code rvunsf and enter your responses there, and reserve the chat box only for questions on the technical questions on the subject. A couple of minutes. Okay, so I see about less than half, or half the people have answered this question. Okay, so this is Bayes rule. Maybe some of you don't know Bayes rule, so let me not take too much time and wait for it to show you the responses. 0.599 seems like a very common answer. I believe that's correct as well. So let me just show you how this works. So Bayes rule, if you've not seen before, this is how you use Bayes rule. It's very, very easy rule. Okay, so you've already seen it in a different form, except that you may not have realized it. I gave you the AND rule. You just repeatedly use the AND rule in two different ways, you get Bayes rule. Okay, that's it. Bayes rule and AND rule are actually the same. They're not different, but it's just it's stated like that, and people get confused. Okay, so probability of event 1 and event 2. I gave you probability of event 1 times probability of event 2 given event 1, right? there's no reason why you should put event 1 first and event 2 second, right? You could have event 2 first and event 1 second. Even there's nothing, I mean, this is just event 1 and event 2. It's exactly the same as event 2 and event 1, right? There's nothing wrong with that, right? So event 1 times this is equal to probability of event 2 times. So this equality, right? The equality of these two things on the right side is called basis rule. It's a very simple rule, and you can use it very effectively in problems like this. Okay. So the question is asking for the conditional probability of the person picked being male, given that they are left-handed. Okay, so this is what is being asked. So let's look at this base rule. Put in event 1 equals male and event 2 equals left-handed. You just plug it into base rule. That's it. P of m times P of L given m equals P of L times P of m given m. Okay, so P of f is P of m is 0.55. That's given in the question. P of L given m is given in the question, 0.11. P of L, what about P of L? It's not really given, but we know how to calculate P of L, right? We can calculate P of L. We know how to do it. We know how to write L in terms of the other events, and we calculate P of L. That's easy to do, right? So L is MNL or FNL, and P of L is just this sum, and then you do this, you get 0.101. That's correct. So once you know P of L, you can find P of M given L. You get this. Okay. So this is 0.599. This is base rule. Okay, so base rule is very to the 100 important. It's used over and over and over again in statistics in so many different ways, and you should get very comfortable using it. Okay, so whenever probability of event 1 given event 2 is difficult to find, but probability of event 2 given event 1 is easy to find, base rule is your savior. Okay, so it will come in and help you wonderfully to get the correct answer. Okay, but again, I mean, it's just one more rule, and it's the same rule, right? So Akshay has asked the question, how to identify base question. So let me just go back and comment on why this is a typical, very good base question. So the conditional probability of being left-handed given male and being left-handed given female is easy. It's easy in the sense it's given in the problem. It's given. What the question asks you to do is the conditional probability of being male given that the person is left-handed. So anytime one direction the conditioning is easy, in the other direction the conditioning doesn't seem obvious, you can use base rule. Okay, and that will work. Right. So that's the base rule problem. Okay, so there is just a prelude. We're ready to do Q4. We did 2 preludes for Q4, and finally the Q4 is there for you. This is we go back to machines and screws being defective, and the question asks for you to find the conditional probability. Notice how I've skipped the word conditional. Okay, this is the same situation as before, right? 3 machines making screws and defective being some percentage. If a screw is chosen at random and found to be defective, given that a screw is defective, what is the conditional probability that it is made by machine 1? So now this word conditional is usually skipped in most of the questions, and that's okay. That's sort of accepted. So when you say if something is true, find the probability, you're actually asking conditional probability. It's not rigorously okay, but it's acceptable, right? So, and once again, like I said, most people would accept this question. They would know that this is conditional probability. Okay, so I'll give you a couple of minutes to answer this question. So once again, don't put the answer in the chat box on WebEx. You go to joinpd.com and put in the code rvunsf and put the answer there. Okay, so there's about little less than 50% of the people have put in the responses on Join PD. I want to give one more minute, maybe a couple of more minutes, give people more time, and let them put in the responses. Okay, so in the interest of time, let me show the responses and see which is very popular. It looks like 0.108, 109, 10869. Yeah, seems like a very popular response. Most people have got it, have got that right. Let me see, 04, 1.22. Okay, once again, I want to point out a probability, if you calculate it and it ends up being less than 0 or greater than 1, you've clearly made a mistake. Don't put that answer in. Probabilities have to be between 0 and 1. Keep that as something that you remember. So this is a clear giveaway. If you get an answer that's negative or it's greater than 1, clearly that's not a probability, right? So somewhere you made a mistake. These rules I gave you, they will never give you an answer which is not between 0 and 1. If they do, then you're using it wrongly. Okay, so keep that as a reminder. It's important. I mean, it's not like a idle thing, you know. I mean, a lot of experts will do calculations and the probabilities will be greater than 1. Okay, that's when they'll know they made a mistake. So keep that as an important reminder. 0.108 seems like a popular answer. I think it's correct. So let's go through the solution real quick. It's just a direct application of Bayes rule. So probability of M1 times probability of defective given M1 equals probability of defective times probability of M1 given defective. This is direct application of Bayes rule. We know 0.25 is probability of M1. We know defective given M1 is 0.01. Probability of defective is 0.023. This we calculated in the previous prelude. And so probability of M1 given defective is just a plug-in. You get 5 by 46, which is 0.09. Okay, so I think that's it for this session. Thank you very much for being a part of it. Let me just put a little prompt here for you to put down your temperature check. If you like this session, drag the blue dot to the green. If you were anywhere in between or you didn't like it, feel free to put the blue dot in the red side. In the meantime, let me go through the chat and maybe we don't have too much time. There's another session coming up at 4, which is English. So we don't have too much time. I'm talking about a chair and a table. One chair and table. Something else. Okay. So uh, the slides will be given to you. They will be shared with you. Don't worry about it. The video is also on YouTube, so you can see it anytime you like. It's no problem. Okay, so I think Abhishek Gupta really wants me to say something about the combinatorial way of answering the balls and red and blue balls question. And people are typing so fast that this question keeps escaping me. Maybe Abhishek, did you send anything privately to me? Maybe you did. Okay, yeah, that is this one won't go. This one is going. A lot of people are sending me private messages. And wait, it's difficult to see this. So sorry about that. So uh, should I do some questions, open questions from 2, 3 people only? I can take. Not too many, right? Stop here today. Okay. Okay, so I think I mean it's a very short time, and I don't want to take open questions. This time, a lot of people are asking for something similar for counting, right? The combinatorial part of it. I think your previous quiz had a few questions on counting and different types of counting, and we'll think about it, and we'll come back to you with a session on that if possible. Okay. So what we are planning, let me just tell you briefly, and if these sessions are really nice and you give us very good feedback and you really want more sessions like this, we are planning to do one such session every week for the graded assignments. And we are planning to do one such session before the quiz, revision for the quiz. So maybe one session on the mock test time, right? So we are planning to do that. So a lot of it depends on how the sessions are worked out. I believe the timetable has been sent to you already or no? Next 2 weeks alone, it's been sent. We'll share a more detailed timetable as we work it out. So you should have these sessions coming at you quite regularly. Okay. So thank you very much. Thanks a lot to everyone who participated. Quite a few of you have said that you like this session. Of course, there is a few who have said you didn't really like it. I don't know. Maybe we'll reach out to you, or you can send us an email as to what you thought were not right, because there's a huge, large majority which has liked it, and there are 3 or 2 people who have said they didn't like it. So if you didn't like it, or what you didn't like, you can write to us by email. And we'll look at the grievances. Okay. So thank you very much for participating, and all the best. Enjoy the English session that's coming.